This is Kosmographia, the Randall Carlson podcast. Welcome back, ladies and gentlemen, to Kosmographia, the Randall Carlson podcast. I am Russ, and we are joined, as always, by the usual suspects. We got Mike, the normal guy, with us. Bradley, how you doing, sir? Doing good?
Yeah, pretty good. Drove in from Atlanta today, so a little weary, but I'm coming back.
All right. Yeah, that's right. You went down to visit with Randall and have some steak, go on some excursions. Yep.
Tried out some new menu items at the Wheelhouse Pub down there, and had a meeting with How-To Mike, came in from Oregon. So, had a very productive weekend.
All right. And Randall, I thought the last week's show with Dr. Lesemann was fantastic. It was like a crash course in drumlins and subglacial flows, and man, it was amazing.
I knew it would be good.
Yeah.
I knew it would be good. Yeah. The man knows the stuff. I thoroughly enjoyed it. I learned some things, and contrary to some rumors that are going around, no, I don't know everything. In fact, as it turns out, I only know a very small part of a small part of a small part of everything. So,
ouch, making us feel worse.
I'm at least 3 orders of magnitude down the hierarchy from
everything.
Okay. Let's put it this way. I'm like 3 orders of magnitude down from omniscience.
Okay.
Yeah, omniscience.
Yep.
Yeah.
Yep.
But I'm working on it. By the end of tonight's show, I may have moved up a rank.
Yeah. All right.
3 orders of magnitude down from infinity is not very much.
That's right. It's still a really large number, I feel like. Yeah, it's got a lot of zeros after it.
Well, Russ did give us a little lesson earlier in orders of magnitude. We really like that. And his struggles.
That's right.
And we determined that the hierarchy, the rank would be pretty simple if you just remembered the Greek prefixes, right? From billion to trillion to quadrillion to pentillion to hexillion to septillion to octillion. And then what?
Nonillion, decillion.
Decillion.
And then after that, it gets interesting. Undecillion, duodecillion, tridecillion, quattuordecillion, quindecillion, sexdecillion. And then it starts doing months. Septimdecillion, octodecillion, novemdecillion, vigintillion. That was as high as I got.
So, when do you get to a jillion?
That was way down the list. Fortunately, I didn't have to go all the way up to a jillion.
Okay.
So, yeah.
Okay.
But
that's where Google comes from. Google is the number with 100 zeros after it.
That's right.
Yes. 100 zeros.
Googleplex.
So,
hearing that back in physics class in high school.
Oh, yeah. Yeah, that's right. So I'm working on some stuff for secret teachings of all ages, and a very, very, very large number came up in the text of the book, and I was having to read it. So I had to go and learn how to say the number properly using all of those terms.
And did you?
I did. I read it correctly, and it was highly entertaining to do it. Mm-hmm. When you get to rattle it all off with, 543 or 672 in front of each one of those things and just keep going on and on and on until you finally get down to trillion.
Yeah.
And then you say
a mere trillion.
Yeah, a mere trillion combinations, right? That was how many combinations it could be. So it's a fun project. Yeah.
So that's what you were looking, this was combinations.
Yeah, it was a determination of how many possible combinations are there with 50 objects.
Okay.
Yeah. It's an enormous number. So.
Okay. Well, I'm glad you clarified that for us, Russ. I was wondering.
Why were you doing this, Russ?
Don't ask you to do it from memory, though, right?
That's right.
So,
not yet.
Yeah.
So, back to Jerome. I thoroughly enjoyed it. And I did note as we got into it, he kind of issued some caveats at the beginning, which was good, saying, that this is by no means a consensus. There's no consensus around the information he was about to present. He kind of made that clear. Did you pick up on that? Yeah. And then at the end, after showing, we see the micro scale. That was another thing that came through to me that was really interesting was the scale invariant. He didn't use that term, but he did use the term an analogy, which would apply because the analogy between one scale of phenomena and a totally another scale of phenomena, and yet within that there's a say a constant of proportionality. There's this invariant nature to the scale of things, and particularly with water erosion and deposition, is that, a small amount of water will create the same type of landforms that you see created by a very large amount of water. So we saw examples that he showed us of things that would be really, in a millimeter scale context, in a meter scale, all the way up to many kilometers. And then ultimately, we saw that we're looking at a phenomena that's really almost continental in scale. And this is where I think he kind of, as I'm sure Brad will have said too, I mean, as we're going through this and learning about this, it's one thing you spend, a week out in the field, you're down on the ground, you're looking at this stuff, and it's an enormous scale, an enormously impressive scale. And yet then when you take a stand back, when you pull yourself back and you realize, my gosh, we're looking at half a continent here. This is, like Jerome was expressed towards the end, this is really a truly impressive volume of water if, in fact, all of these features are, in fact, created by flowing water, particularly water flowing subglacially under pressure. We're kind of confronted with a phenomena that is going to be extremely interesting to try to explain. But if we could go in a time machine back and maybe hover just outside of, right outside, maybe a couple of thousand miles up in orbit and watch what happened, I think we would be seeing something that would be on a pretty extraordinary scale. Something happened to this planet at the end of the last ice age. It's just that we're only beginning to visualize, and it's just on a scale that's just staggering in its immensity. So there's a lot of room, I think, for some rigorous investigation about this, because the point is it's not settled yet. I mean, Shah's work opens a whole doorway onto a whole nother level of thinking about this phenomena. And I can certainly understand the resistance that it's getting because the implications of it are so profound. I mean, what Jerome showed us with that map and the flow patterns, it's 3/4 of the ice sheet. And the other point he made was that the flow forms seem to be emanating from discrete epicenters, which I think is, we have to, because in the old models, you've got glacier recession, which is shrinking back, right? And we know that happened to some extent because the moraines are there. You can see recessional moraines that show that there were, retreats of the glacier that were somewhat orderly, and there were pauses, enough of a pause that it could build another moraine, and then there was another recession. But then juxtaposed on that is this whole other phenomena of these massive hydraulic events. And this is where it gets really interesting to me, because when you start talking about peak discharges of, 400, 500, 600 million cubic feet per second, that is completely beyond the scope of anything we've seen, on Earth in historic times. And when you begin to realize, and as we're going to get in explore in upcoming episodes, when we begin to see that the global nature of some of these events, and I say global, I mean, because we can go to Europe and we'll find very similar things. We'll find huge tunnel valleys. We'll find recessional cataracts. We'll find slot canyons. We'll find gigantic boulder deposits all over South America. Many places all over the planet display the effects of megaflood phenomena. So once you start beginning to really appreciate the scale of this, two things come. One, if there were people in these regions when this stuff is going on, they're probably not going to be too many left after it's over. The other thing is that a phenomenon on this scale would leave such an impression on survivors that you can clearly understand how it would then become a tradition that could get handed down for generation after generation. And the fact that, from all over the world, you have various groups of people, various ethnic groups, various religious groups, various, who have these traditions of these tremendous floods. I mean, several hundred have traditions of these gigantic floods. Now, in the Judeo-Christian tradition that we've kind of taken, sort of for granted, we're all growing up and being taught the story of Noah and the flood. So everybody in the Western world is going to know the story of Noah and the flood. Probably fewer of them are going to know the story of Xisthus and the flood, or Deucalion and the flood, or Utnapishtim and the flood, but everybody's going to know about Noah and the flood. And the story of Noah is very consistent with the others in a lot of details. There are unique differences, but there's a lot of details that are the same. But what you get at is that, and this is the thing I think I've been trying to hammer away at for decades now, is that survivors of a flood of 500 million to 1 billion cubic feet per second, as far as they know, the world is done. It's over. It's destroyed. If you're lucky enough to somehow have survived, in the entire world you knew is gone, washed away. As far as the eye can see, as far as you can travel by foot over a course of months, if your former world is gone, it's erased, the world is destroyed. And that is a story that's going to get handed down and handed down and handed down. There's nothing pseudoscientific about looking at the ancient traditions of great floods and going, hey, we might be able to learn something here about this phenomenon that we're now seeing, glaringly obvious in the global landscape that was not really visible except, in a limited fashion 100 or 200 years ago. And when you look at some of the early, which brings us to another point, which is interesting. When you look at the early geologists, the founding fathers, if you will, of geoscience, going back to the early 1800s, people like Sir James Hall, Cuvier, Buckland, Adam Sedgwick, Roderick Murchison, and probably at least half a dozen others, the ones who you would go, okay, these guys collectively created what became the academic science of geology. Almost to a man, they were catastrophists, because they would go out looking at the landscape like, Sir James Hall in England. He would go look at the Thames River and he'd see a case of an underfit stream. And he'd go, what is the relationship between the river that's there, which is, it's a pretty good sized river, compared to the channel that it's flowing in, which is huge? Well, is that... And of course, when they started thinking about that kind of stuff, one of the things is that most of the models of Earth history were, nobody was thinking in terms of millions, much less billions of years of Earth history. So you would automatically assume, that, well, if the Earth is really not that old in terms of millions of years, well, now if you've got, what the old Earth did was it allowed uniformitarian gradualistic processes to create big channels. You see, big channels, because now you got enough time that you can erode it a little bit here, a little bit there over millions of years. Now you got a big valley and the modern river that's flowing in it. If you're thinking that the planet or the world is only 6,000 or 7,000 years, you see, now you don't have a lot of time to do that. So how does the big valley get there, the big channel? Well, it has to be cut catastrophically, and it would be natural to go and assume, if you're, indoctrinated into the Judeo-Christian tradition, that, this is obviously evidence for Noah's flood. But for most of these guys, some of them, like Adam Sedgwick, he was a theologian. I think James Hall, who wrote on the revolutions of the earth, a famous book, and it was essentially about that. It was a book on catastrophism. I think he had a theological background, theologically trained. But some of these guys did look at the world through a biblical perspective and did believe that they were looking at giant flood features. Others didn't necessarily come from the biblical perspective, but still saw mega flood features. So the thing is that whether you came to it from a biblical perspective or not, and you looked at some of these formations and you thought this is evidence for a giant flood, as it turns out, ironically, 2 centuries later, is they were right, or mostly right. Now, their initial perspectives essentially got superseded by the rise of Lyellian gradualism, which was Charles Lyell, who was basing his work on the James Hutton and I think it was William Playfair. Those 3 guys are pretty much what gave us the concept of gradualism, or what came to be known as Uniformitarianism. And I think it was Charles Lyell that coined the term, the present is the key to the past. So in order to understand the past, we look at processes that are going on today, and we extrapolate backwards, and thereby explain these features and formations that originated sometime before humans were able to observe, right? And it has been a very powerful and effective tool for understanding and decoding the past. The problem is it became dogma. By the early 20th century, this had become dogma, and it was being taught in the academic institutions that have now, that are now teaching programs of earth science, of geology. Whereas in those early days, when it was Cuvier and Buckland and Murchison and Hall and all those guys, there was these guys were not even called geologists. They were considered natural philosophers, right? So by the time you get around to the late 1800s, early 1900s, you now have these dogmas that are being perpetuated, and uniformitarianism was one of them. And the problem with dogmas is that usually they're based upon something that was true at the beginning, and usually still is, but it becomes so entrenched that you're not allowed to go outside the framework of that dogma. And that's what happened to Earth history models from a good part of the 20th century, is that and this is why J. Harlan Brett's encountered such resistance to his great flood idea, as we've talked about, is because you had an entrenched bureaucracy by the time he came along that was afraid of, if you start talking about these giant floods, you're going to drag us right back to biblical diluvialism, and we don't want to go there. We're done with that. We've evolved past that, see. But it's come full circle. That's the point. And what we get to in the last 2 decades of the 20th century, I think, is the revival of catastrophism. And it was triggered by, I think, the 1980, publication of the Alvarez paper, which galvanized a whole new way of thinking about the possibility of great impacts from space. So, where that has gone is, a lot of initial resistance. No, we don't need something from space to get rid of the dinosaurs. But as it turned out, yeah, we did. We needed something from space. Now, it may have been helped, and probably was helped a lot, by volcanism, enormous volcanism, the volcanism that created the Deccan traps. But as it turned out, and then the objection was, well, look, if you're going to invoke something from space, you got to have a crater. If you don't have a crater, get out of here. It was just like the critics of Brett said, well, if you can't provide an origin for these giant floods of yours, well, get out of here. We don't want to hear about it. You got to come. And so same thing with Shaw. If you can't come up with a viable mechanism for producing that much subglacial meltwater, get out of here. There was no subglacial floods like you're talking about. The drumlins and all of these landforms were produced in some vague, indefinite way by the glaciers themselves moving over and reshaping the till. But see, here's the problem. You got glaciers moving across the landscape, grinding up the landscape, creating the layers of till, right? Well, they're certainly fully capable of doing that. But to get from just a distributed ground mass of till into these elegant drumlin shapes, I mean, that's where it gets complicated. And that's why there's been 100 different theories. Now, Shaw comes along and says, wait a second, all these features that we're looking at, they have all the features of water erosion and deposition. Oh, fine, that's cool, except for one big problem. And that problem is the scale of the phenomena that you're looking at. Look, if those drumlin fields are caused by flowing water, then that's a hell of a lot of flowing water, and you can't account for that, so get out of here. Don't bother us. We got it figured out. Some way we're tweaking it, but we got it down to where we can say that it's being reshaped by the glaciers moving over the till. And as we saw with Jerome's presentation, when he gets to the end, I mean, did you guys pick up on that? He was maybe struggling a bit to wrap his head around the scale of the evidence for flooding that he had just presented to us.
Yeah.
Yeah.
As we all do.
As we all do. Yeah.
Right. Yep.
Yes.
As we all do.
He's kind of in that academic constraint though, where he has to not speculate too far out.
Right.
Kind of stay within some bounds.
Yes. And us being a
but
bunch
I think when we have him back, or I'm sure when we have him back, we're going to kind of let it go free with the both of you and just say, okay, well, what if though?
Sure. Why not?
So that'll be fun.
Yeah, I think so. So yeah, I think that well, and he pointed out, I mean, I think one of the upshots of it was, is as much as I've learned over the last 20 or 30 years, I realized, man, there's still so much more to learn. To come up with, what I think is a coherent explanation. But here's one of the things I think it'll start with is really mapping, which he's already got a great start. We saw the map that he had, but what we need is a little more detail. We need more, a closer look at the forms, because what it was apparent was that you had these meltwater flows that weren't originating from the margins of the ice sheet necessarily. So several of the things that I read in, John's last papers when, he was being attacked by the critics, like, the critics, and if you read the criticisms, the papers critical of John Shaw, they basically, the criticisms all pretty much boil down to, well, you can't provide a source for the water. So, therefore we got to look at something else. And John did try to come up with various sources, but even in those sources that he tried to come up with, there are implications. Like he talked about, well, maybe there was a ponding on the surface, supraglacially, right? Well, yeah, but then the critic said that would be, and then this ponded water reached a point where all of a sudden it accessed the base of the ice sheet, right? And ice being denser than water being denser than ice, once it accesses the base of the ice sheet, it's able to lift up, decouple the ice from the landscape and flow under, right? But then the problem was, where did all the superglacial water? Because the Livingstone Lake event that we're going to talk about, he estimates 84,000 cubic kilometers of water. 84,000 cubic kilometers. That's that is roughly 20,000 cubic miles of water. And that is roughly 35 times the volume of water in one drainage of Lake Missoula. So that's a lot of water. And that's just one. That's one event. What is termed the Livingstone Lake event.
How much water was in the ice at the time?
Well, at the time, see, that's where we can go back to the late glacial maximum, and we got it at an end point, and we can say, okay, there was about 6 million cubic miles of ice.
Okay.
Then we can go to the glacial termination at about 8,000 years ago, and they can say, well, if we consider the Holocene amount we set that as our baseline, and we set that as our 0 point, if we say that's 0, because now all of the late Wisconsin ice is gone, and what's left is a Holocene ice, okay, then you've got to go from 6 million cubic miles of ice at, say, 15,000 years ago to 0 ice at 8,000 years ago. Now, in that process of getting rid of 6 million miles of glacial ice, cubic miles, do we imagine a process that's uniform through the entire, say, 6,000 to 8,000 year sequence from beginning to end? nice smooth curve? Do we imagine something that starts out slow and increases to some peak and then slowly tapers off?
No.
No.
There are pulses, right? I mean, there are meltwater pulses. So
I think we have to be looking at something, that it's maybe starts off in a kind of a normal sequence, but then we have this meltwater pulse 1A, where suddenly there's this massive influx of fresh water to the global oceans, whose only source can be the ice sheets, right? So you've got what you just said, Kyle, is rather than a nice, like a smooth bell type curve, maybe we've got something with a lot of pulses, or at least a number of pulses. But it's still problematic, because how do you produce those pulses? That's where it gets problematic. And so we've got this 14,600 year event, assuming the dating is correct. And for now, I'm going to assume the dating is correct. Although I'm going to hold open the possibility that in the nature of these events that were occurring then, some of the dating methods may get affected, whether it's optically stimulated luminescence, which depends upon cosmic ray bombardment, right? Whether it's radiocarbon dating, which depends on the amount of radioactive carbon, et cetera. There may be things that introduce uncertainties, inaccuracies. So that would be something that I would not rule out. But for now, let's say that there was a meltwater pulse 1A at 14,600. There was meltwater pulse 1B at 11,600. So there we've got a 3,000 year window, and right in the middle of that is the Younger Dryas. And now we're finding the impact proxies at the Younger Dryas, right? Well, it also appears that there was a major discharge flood from Lake Agassiz right at the Younger Dryas, which then brings us back to the question of Lake Agassiz. And what was Lake Agassiz? Well, Lake Agassiz was this giant meltwater lake that wouldn't have been there during the late glacial maximum, because the whole area occupied by Lake Agassiz was under ice. So somewhere during that, and Mike brought this up before we started recording, what was the age of Lake Agassiz? And I was trying to say that, well, it's indeterminate. We know that probably before 14,600, it wasn't there. And we know that somewhere between 9,000 and 10,000 years ago, it wasn't there. Now, in between there, it was there at some point. How exactly long was it there? How exactly big was it? These are still being worked out. But one of the things that's become apparent now is that there was a major discharge event at the Younger Dryas boundary. It may have gone up the Lawrence Seaway, and it's also apparent that a major discharge went north throughout the Mackenzie River Valley into the Arctic Ocean. So now here's the question that I would raise. How long was there, how long of a span of time was there between the initial accumulation of this water that wasn't there, say at 15,000 or 14,600, that wasn't there, but was there 12,900 to the point where it could have these massive, and we're talking about discharges in the scale of Missoula flood. We're talking about 300 to 400 million cubic feet per second. So that's the issue. Now, one of the things I would look at is go, well, maybe Glacial Lake Agassiz was much more short-lived than a lot of the assumptions. In fact, the assumption would be, well, to get 84,000 some cubic kilometers of water, well, let's see, what was the maximum volume? While you're there, Kyle, look up Lake Agassiz, and I should know this by heart, but tell us the volume in cubic miles or cubic kilometers. We'll convert easily enough. So what the question I would ask then is, how long between the first initial accumulation of this meltwater and the point where it had this massive meltwater discharge at 12.9 at the Younger Dryas boundary? What I would propose that we consider is that time was actually very short.
Well, I was just going to say on many of the sides, I guess, or the shores, it's up against the glacier, right?
Yes.
But then maybe a third of it, I don't even know without really checking the maps. It's held in by the topography where the glaciers have already melted.
Yes, you got that exactly right, Brad. The eastern.
So there's not a bunch of ice dams along the perimeter of the lake.
Right. Pretty much most of the eastern shore is against the ice,
Right.
the receding ice of the Laurentide ice sheet. But you've also got the topographical situation because of the isostatic depression adjacent to the ice. So you've got the waters ponded in that depression. So clearly, some of the later stages of flooding are going to be as the ice core melts away and the water begins, and the ice begins to rebound, you're going to have a whole succession of spillover events, probably stretching out over, 2 or 3 or 4,000 years before all that water is finally drained away.
They're showing, they show area and depth and stuff, but
they don't show the volume. What's wrong with those?
I don't know. Yeah.
Put in Lake Agassiz volume.
That's what we have
done.
And we
you
tried
did
max,
that?
Yeah, we tried max volume too, and we're still not finding it.
Here we go. Okay. The volume was
Approximately
what is that?
13,100 cubic kilometers.
Cubic kilometers, yeah.
Aha. Okay. Wow. 13,000. That was maximum volume.
I put in max volume and it didn't. That's what we were looking for before. So I just put in volume and that's what it gave us.
Aha. Okay. Well, that's probably.
It says at the Herman Beach level.
Oh, yeah. So
Maximum depth during the Herman phase was, I lost it.
Well, I think the Herman Beach was the high water level.
Okay, yeah. Maximum depth during the Herman phase was approximately 270 meters.
So there's roughly 2.6 cubic kilometers in a cubic mile. So you said 13,000. So
13,100.
So that works out to be about 5,000 cubic miles. That's a lot, which is roughly, let me see, I said 5,000 cubic miles. And that is about a little over 8 Glacial Lake Missoulas.
Wow.
Okay.
Yeah, 8.3 Lake Missoulas. But these numbers are only approximations, but it certainly get you in the ballpark.
So yeah, and now here on Wikipedia it's saying at its greatest extent it may have covered as much as 170,000 square miles or 440,000 square kilometers.
Okay, yeah.
May have at its greatest extent. So yeah.
So why don't you pull up your graphic?
Okay.
We'll show the people there what we're talking about.
So that's like by far bigger than any lake on the planet now.
Yes.
Oh, hell yeah.
By far.
By far. There we go. Now, the eastern side over there in the northeastern, that was held in by the glacier itself, the core of the Laurentide ice sheet, which was centered over Hudson Bay. And over there to the southwest, it was basically held in by topography and moraine. Because when the ice recedes, it's going to leave the moraine. Moraine can form dams. Now, also remember, because of isostatic depression, which we've been talking about in this podcast since I think the very first episode, you had the land depressed as much as 1,000 or 1,200 feet in the area of Hudson Bay. So the depression of the land now creates a situation where all this meltwater ponds against the glacier. So you have this part of the transition phase is the glacier shrinking, the water volume is growing, and as you get these drainage events and it's releasing weight from the North American continent is now isostatically rebounding. And as it rebounds, there will be a succession of spillover events. And that's exactly what is seen with Agassiz. It didn't all drain at once. But the first drainage was apparently the really big one, or the one at about 12,900, where you had a whole lot of water. And so Yeah, and if you could, let's see, I'm going to have to move my, I've got some things to open here, so I can't see the whole picture. Okay, so if everybody looks down in the lower right-hand corner, you can see Lake Superior down there. And you'll see that Lake Superior, anybody who's traveled up there around the Great Lakes will know that Lake Superior is one hell of a lake. It's a really big, very impressive lake. But look at Lake Superior compared to Lake Agassiz. It's minuscule in a sense compared to Lake Agassiz. Lake Agassiz was a phenomenal body of water, and it's, of course, fresh water. And I mean, it would take you literally probably weeks to sail across it. You couldn't stand, on the eastern or western shore, say, and see across to the other side, because you're looking literally at a giant, like an inland sea of fresh water.
It's now Lake Inferior.
Lake Inferior.
It's like a pond compared to that Agassiz.
Yeah, right. And there were several outlets. And what was the exact chronological relationship to these outlets is still being worked out. But the one we visited with Graham Hancock, which we talked about, was the southern outlet, which discharged into what is now the valley of the Minnesota River. And you can see that way down at the bottom of the center of the screen, that tongue of the lake that comes right down, and then you see the channel of the Minnesota River Valley coming off of there. And right at that mouth is where Big Stone Lake is.
So to put this in perspective a bit, if what Wikipedia said was right about the greatest extent of the size of Lake Agassiz, that's bigger than the state of California.
Yeah, bigger than, wow.
Sure.
Yeah, because California is 150,000 square miles. So if it was 170,
what is the area of Texas?
Texas is 261, so it was close.
Oh.
Yeah.
That's a lot of water, boys.
That is a lot of water. Bigger than California.
Bigger than California, right? Wow.
So, and then you said maximum 270 meters deep.
In depth, yeah.
Yeah. So pushing 800 feet.
Almost 900. 885.
Okay. Yep. Crazy.
And the depth of Lake Superior is what, about that, I believe? I've looked this up. I should know.
I can find out.
It's around 1,000. I can't keep all those
Around
different
1,000.
lakes straight. Yeah.
Yeah. Lake Superior is the deepest of the 5 Great Lakes.
Right. Well, it's got those channels south of
Yeah.
Nipigon there. Yep.
Yeah.
1,332 feet is the deepest part of Lake Superior.
Okay. So referring back to my previous question about, the sequence or the age of Lake Agassiz, is it sitting on top of the ice? Is it sitting underneath the ice? Is it sitting on the ground where the ice was?
Where the ice was.
Okay. So it's post-glacial.
Well,
you said concurrent earlier.
Concurrent, yes, because you've still got a very large mass of ice centered over Hudson Bay. You can figure if from the maximum extent that let's just to keep it easy, it shrunk to 50% of its original size. Well, in that shrinking, it's because it's melting, right? But also because of the fact that the heavy weight of the ice sheet has depressed the land in this bowl. As you melt the ice, then water is forming around this bowl. Now, around the ice core that's in this depression. Well, the only place it's going to be retained is on the western side, because the eastern side is the Atlantic Ocean. So meltwater that's pouring off of the eastern side is just going right into the Atlantic. But over the western side, it's pooling up in this depression that is immediately adjacent to the ice sheet. Does that make sense, Mike?
Oh yeah, that's fine.
Okay,
I was wondering, is it super glacial but it's not. It's they're probably chunks of ice within Lake Agassiz though.
Oh, I would bet
there are bergs floating in. And
yes, good point, Mike. That's an excellent point. You get at least, I would say, 2/5 of an attaboy for that.
Ada.
because you're going to have undoubtedly an enormous number of icebergs floating in that lake, especially if Agassiz was, as I am beginning to suspect, not the result of a protracted melting event, but was in fact the result of a sudden melting event. Then you could, I think, look for evidence of there being enormous numbers of icebergs.
Yeah, and
it starts as a slushy and
Yeah.
slowly turns into
That's
more of a lake.
precisely
iceberg.
the metaphor I was looking
Yeah.
for, Kyle. Yes, Kyle.
So does the I was seeing on that map we were looking at that there's different shorelines, and they seem to be the shorelines that are south. So is the northern shoreline pretty static for Agassiz, or does it also fluctuate a little bit?
Oh, it would fluctuate. I mean,
Okay.
particularly when you have the drainage events, like the Herman level being the high level, and you have the catastrophic drainage, the level of the lake drops significantly. So
Right.
now it's going to form a whole new shoreline.
Okay.
And so going back to the late 19th century, a lot of what the early geologists were doing was mapping the shorelines of Agassiz. And, you know, and it's not like a nice, continuous, very obvious shoreline. You have to, you find a piece of it. And then you might go 10 miles away and you find another piece of it. See, the other thing that confuses is that they go, wait a second, there's 10 feet. This is at 10 feet or 20 feet higher than that other piece. Well, that's where isostatic adjustment comes in. Yeah.
We can't be sure that I think you talked about this a couple episodes ago, that rebound is not just slow and constant, that there were sudden surges, because we've got those places around Hudson Bay where there's obvious shorelines. So you'd think if it was slow and gradual, you wouldn't have these distinct shorelines. Okay, it jumped back up, stayed there temporarily, made a shoreline, rebounded, made another jump. Versus a slow, gradual lift.
Exactly. And it does appear that there was some seismic jerking in the particularly initial stages, because if you look at those shorelines around Hudson Bay, what you see is that the largest differential is, towards the bottom or towards the top, where it would have moved up to a larger increment and then slowly got smaller and smaller as it made its adjustment.
Oh, yeah.
Okay.
Do you want to look at the historical map of Agassiz, and then we can make
let's do. That would be great.
Okay. And then we could take a break afterwards and come back.
Mm-hmm.
Yeah, there it is.
And you'll notice it's much smaller.
Much smaller.
Let's see. Are you able to? Can we see the southernmost terminus? Are they showing it at the same place? Yeah. Look, see that where it says Big Stone right there? Yep. There it is, Big Stone. Yeah. So that's pretty much close. I guess they had figured out that was the southern outlet. But yeah, you can see that between the two graphics there, it has increased in size because they found
farther out. Yeah.
Yes.
Shorelines. Yes. Wow.
Exactly.
That must be you're like, okay, here's a glacial lake shoreline. And then you keep going around and then you figure out, wait, this is the same lake that I was looking at way down there.
Yeah. So here's
hundreds of miles away.
Here's Lake Nipigon, way far away.
Yeah.
From the shore there. And then you go to this other one. And Nipigon is here, and the lake's going past it.
Yeah.
So, yeah.
And notice the arrows. Is it possible for you to zoom in on Nipigon? There we go. All right. So I should have gone ahead and colored Nipigon. I can do that in the future, though. But yeah, you notice you've got what appear to be three pathways coming off of Agassiz, headed towards Nipigon. And then you've got these arrows coming out of Nipigon, connecting Nipigon to the basin of Lake Superior.
Right.
Now, I think it's very clear when we've looked at the topography of this zone between Nipigon and Superior is that we're looking at channel scabland phenomena. We're looking at catastrophic flood, erosion, and deposition. what is the connection between that flooding there and the flooding of Agassiz? That's a question that we got to come back to, because Agassiz really does provoke some real questions about the nature of the deglacial process. And notice, let's see, can we find Lake Hind Basin on there? Let's see. We're right. Okay, zoom in. Okay, see North Dakota? If you go straight above North Dakota, you'll see an arrow pointing in. Yes, right there. Now check that out. This is the area we've been looking at. I believe that's going to be pretty close. Let's see. Yeah, North Dakota. Yeah. There we go. Yeah. This is, we can't quite read it. The resolution is not enough quite to read it, but
yeah. Brandon right there. You just kind of underlined. Yeah, that was just in the outskirts of it. Right. That's right. So that's the area right there where Hind was, see? And Hind was initially separate from Agassiz, and then eventually it received enough influx of meltwater that it overflowed into Agassiz and created this massive delta fan. And actually that delta fan, I'm guessing, is what this, if you go back in, you'll see there's this darker area spread out. Yeah, that would be it right there. That would be it. So one of the things we've been looking at in terms of these huge glacial spillways in the last couple of classes before Jerome joined us was meltwater flows away from Agassiz and flowing like down towards Minnesota, North Dakota, and meltwater sluiceways flowing into Lake Agassiz. So the water that flowed into Hind then overflowed into Agassiz.
One last question before we go to break, and you can answer it after the break.
Oh.
What is the relationship of Lake Agassiz to Lake Missoula?
Good question.
I have a question also that I was going to ask before break, but it's up to you. Yeah, it's you kind of touched on it, but yeah, I don't want to drag us away from Mike's question, which is a good one.
Well, yeah, the relationship. You mean geographically? I mean, they're two totally distinct bodies of water.
Right, but does the larger one, does Agassiz feed into Missoula? But like I said, we can get into after the break.
No, it does not. It does not.
It's on the other side of the continental divide.
Yes.
Okay.
So Agassiz is draining into the Atlantic, it's draining into the Gulf of Mexico, and it's draining into the Arctic Ocean, but it is not draining into the Pacific. Lake Missoula is exclusively draining into the Pacific Ocean.
All right.
Yeah, I was thinking more about the timing.
Yeah, that's what I was
thinking.
Well,
that's a good question, too.
Yeah.
That is a very good question.
Yeah. Normal guy questions are good.
Yes, normal guy questions are usually pretty good.
They are.
That's why they give me the T-shirt.
Yeah.
You're just not allowed to make comments without having them vetted first.
That's right.
Yeah, that's right.
Well, let me throw my
All right,
question
let's
at
take a
you. If you want to answer it or get back to it at a different time, but you just kind of touched in, and we'll see if I can formulate it again here later, on the history and the early guys being catastrophists even before they were called geologists, right? They were natural philosophers or naturalists even.
Yeah.
So I was reading something about Brett's doing some research with the last couple episodes, and it said initially he was a physiographer. So I'm wondering where that term came in, because that's what's now is considered a geomorphologist, studying physical features of the land surface. So that's what we're doing. We're studying and commenting on geomorphology here, but it used to be physiography. So I was just wondering when that came in. When did that shift to geomorphology? Do you know, since you were talking about the history and Brett's came up?
I don't know the answer to that question, Brad.
Okay. Because I was going to start saying, well, yeah, because I've said natural philosophers. Like, okay, well, I can say I'm a physiographer because I'm not looking under the surface. I'm looking at all these maps at the surface features, but it's like, okay, well, that's not even the modern term. It's now that morphed into geomorphology. So, yeah, I just wondered how that slotted in and when it changed. But yeah, I guess I can track that down myself.
Well, okay then.
Okay.
Physiographer is a great term.
Randall is a
Yeah, I like that.
physiographer.
And that thing over by his elbow there is still up against the door.
Oh, that's right. I see.
Yeah.
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 She just gave up.
Yeah, he did.
Okay. If you're not going to pet me anymore, I'm going to go over here and go to sleep.
All right. Well, it's break time,
Break
folks.
time.
Let's do
We'll
it.
be right
Let's do
back.
it.
That's right.
All right.
Okay.
Welcome back, ladies and gentlemen, to Kosmographia, the Randall Carlson podcast. And once again, want to mention cbdfromthegods.com. This is our sort of a trial balloon for advertising, and we are making sales. So you people out there have been going to the website and ordering stuff, and that really helps us out. It's helping us build statistics so we can turn this into a profitable product. So we thank all of you for patronizing cbdfromthegods.com. Make sure if you go there, put in the promo code RC ships free with whatever you order, and that notifies them that you came from us. So really appreciate that once again. And
Absolutely.
That's
Mhm.
right.
I think both Russ and I have noticed a very detectable effect on our quality of our sleep. Since
Yes.
using it.
So much.
Yeah. And, I think I whined and complained last week or the last episode about the tumble I took when I fell into the chasm and bounced around on the concrete. But so I had some pretty vicious bruises. I have actually photographs, documentary evidence of the injuries sustained. I won't show those, but I have now taken a couple of pictures. I've been putting the salve on, particularly this. I had a bruise that was purple and about the size of a basketball on my left thigh. Now, actually, I exaggerate a little bit, but it was quite swollen, a purple bruise wrapping halfway around my thigh, and I've been putting that on diligently every day. And we went on this long hike, Brad and I, in North Georgia on Sunday, and I pretty much did the whole hike, although towards the end I started feeling it in my left leg. But for the most part, the healing seemed to be remarkably fast, considering for the first day or two after the injury, I'm thinking, oh my God, am I going to have to get my leg amputated? I mean, is this going to... But that didn't happen. So I think that, and then I got to also say, my wife, Julie, is still using it on her hands. And she said today that she absolutely loves the product. And this was an unsolicited, because we got another batch in, and she said, where is the new salve? You got some new salve, didn't you? And I said, yes, I did. Here you go. It's in this cardboard box. It's yours. Go for it. So, yeah.
Well,
Yeah,
I'll
I can
add
say,
also, Kyle, excuse me, that it's helping me sleep also. I've been doing the half dropper in the middle of the day for some clarity and, just mellowness, and doing the other half dropper before I go to bed. And I thought I slept excellent. But typically, no matter when I go to bed, I would wake up at first light, and then I'd kind of be back and forth. And now I've using this in the past 2 weeks now, I'm actually sleeping straight through, an extra hour and a half before the first time I wake up. So, I mean, I notice a difference too.
And I think, that's some of your most important sleep too. It's those last couple
bits.
hours. Yeah.
Yeah.
Definitely.
So, okay. Well, enough of that for
Good
them.
reports all around. CBDfromthegods.com.
So we were talking about Lake Agassiz, the drainage. I got a few pictures I'd like to show here. All right. So we looked at this 2 episodes ago. See these rounded off. Now, this is not something that's so dramatic you're going to have to pull over and get out of your car and go, oh my God, look. But this is all part of understanding the diverse nature of this evidence. These are whalebacks. And and you can see one right up there at the curvature of the road. There's another whaleback. And what that is, it's bedrock that is first exposed by the glacier coming down, but then when the water rushes off, you've got this hydraulic smoothing that's taking off the surface and rounding the surface of these rocks, you see. So these whalebacks, and you can see in the background here, there's some other exposures, are remnants of this catastrophic discharge. And if we go, let's see if we go to the next one. Yeah, here's a very prominent one. It's really almost drumlinoid. And that's Brad there in the back. This is Graham Hancock. We have just been up on top of this, trying to get because this outcrop is right in the center of pretty much in the center of the outlet channel. So when you go up on that rock, you can kind of get a good 360-degree perspective. When you look to the north, you're looking up into the outlet. You would be looking towards the lake itself. These are some of I had this as a backdrop with when Jerome was on, but now you can see it pretty clearly. These are examples of what's strewn all throughout the outlet, which is these huge rounded boulders. And hence the name Big Stone Lake is because of the presence of these big stones. Here is just below the outlet, and you can actually see the upper section of the Minnesota River. Okay, no, it's up here. Here's the Minnesota River up here. And the outlet, the channel outlet, if you look down here where my cursor is from here all the way over to here. So you can see that the whole channel width is much bigger than the Minnesota River that's flowing in that channel now. And you can't see too well on here, but let me try to outline them for you. Look at this. Watch my cursor right here. You see this?
Yeah, I was noticing that too.
There you go. There's a streamlined erosional residual. And over here, look at this. You see this point? You can follow it right around like this. Of course, there's roads on here, and you can actually come in. You go past this quarry. This is a gravel sand quarry here, because obviously in the outlet, there's going to be all of this sediment that's been washed through and dumped as this water is gushing through the outlet. But you can actually follow the road around here into this wildlife sanctuary. And so this lake here was one of those lakes that had so many birds on it. But yeah, you can see a streamlined erosional residual right here. And in this, where did it go? There it is. Okay, we were just looking. This was from Kehew and Lord 1986, which is a study of the spillway that we see right here. Here's Lake Traverse. The lake came down, and you can see the two oversized channels that it cut that flowed together right here and then flowed out down this way. And then just below the mouth in the Kehew and Lord paper, they're showing this whole collection of streamlined erosional residuals that lie in the channel. So with this diagram, you can kind of get a better sense of the perspective. Here's one shore of the channel, and here's the other shore, and then it widens out. And over here, this is what you would call a boulder lag. You've got a terrace, and the terrace is strewn with the big boulders, the big stones, like the picture I just showed you. So there's hundreds and hundreds of these, maybe thousands of these large boulders. I'm not sure where they came from. I would certainly, it's one of the things that I would like to find out. I know there's probably been studies on the provenance or lithological origins of these boulders to see how far they were transported. They probably weren't transported that far, but of course, the degree of rounding is an indication of paleo transport distance. But what you see here is that there's a lot of these SERs or streamlined erosional residuals. So I had this one Google Earth image here where you could actually see the very ones that we were just looking at on the 1986 mapping. Yeah, okay, and then here is, Origin. It's from the paper Origin and Large-Scale Erosional Features of Glacial Lake Spillways in the Northern Great Plains, which appeared in the Geological Society of American Bulletin back in 1986. And this is one of the earlier papers I read on megafloods in North America. I probably didn't see the paper the year it came out. I probably saw it 88, 89. I think as I've told the story, I'd been using the Georgia Tech Library from the, say, late 70s to the late 80s. And about 88, 89, I discovered that we had a little science center right here in DeKalb County, and they had a pretty darn good library there. And they were linked into the whole interlibrary loan system with hundreds of universities, in America and Europe, a lot of different places. So once I discovered that and was using the Fernbank Science Library, I was able to access a lot of papers. So there was a lot of papers on Carolina Bays and megafloods and stuff that I started reading about 88, 89, 90. This was probably in that batch. So this is probably, I think I took this right from a photocopy that I had of this paper. But this is where I started really becoming aware of the scale of this thing, realizing, well, gosh, there are scabland features and erosional features on a mega scale right here in the middle of the continent, right where I grew up, right in my backyard. So, but yeah, Kehew and Lord did a lot of seminal work on catastrophic flooding in the Middle West. And I would be not surprised if you could actually find some of their papers through Google Earth. Google Scholar, which, by the way, is a great tool if you're doing research. They don't have everything, but they have a pretty good bit. And there's enough up there that if you're just getting started in this kind of research, you'll have plenty of reading and stuff just from what you can download online through Google Scholar. So let's see here. Then we did look at the mysterious linear features last time, didn't we?
Yes.
Yeah,
yes, we did.
We looked at that
2 or 3 ago, but yeah.
Yeah. So these are pretty bizarre. Now, in trying to explain them, I'm trying to think that perhaps, you can actually get in some floods, if you've got a large enough boulder or rock, or the generic term would be clast in the geological term, which could be swept along. It's not enough. It's too big. The current is not competent enough to actually bring the boulder or the clast into suspension. So what it's doing is it's sliding along the bottom. And if there's not obstructions, if you have a zone where you can get more or less laminar flow as opposed to turbulent flow, perhaps it's possible that water is just moving straight enough that a boulder along the bottom would just. The problem is, though, with that theory is that these things are convex, so they're actually prominences on the landscape and not depressions.
That sounds like a problem.
Sounds like a problem.
And so it's definitely not a function of like the underlying makeup of the material or something. There's not like a rock ridge there or anything. I mean, I know that's strange, but if it's a prominence that to me would imply that maybe there's
no, it's not. It's composed mostly of glacial till.
Oh wow. Okay.
Yeah. So yeah, check this out. So this is from an older aerial photograph that I was able to download. This is basically 2 versions of the same thing. But the author of some of the studies on this is assuming they're somehow related to drumlins, that they're like massively extended drumlin forms. And they kind of are, because in some sense the stoss or upstream end tends to be blunter than the long, tapered downstream end. Here's a couple of them. One of my favorite books that I discovered decades ago, which was Geology Illustrated. We've introduced by John Shelton, who was a not only a geologist, he was also a photographer and also a pilot. So put those three together and you got a whole book of these really great photographs. And it was one of the early books that really devoted a lot of photographs to catastrophic flood features, including the channel scablands. But this is, as it says here, this is the giant Lake Agassiz spillway at the Minnesota-South Dakota border. Modern Big Stone Lake now occupies a portion of the spillway. And so you can kind of really get a sense of the spillway here. If you look over here, here's the bank full part. And then over here, it's a little bit farther away. You've got a little bit more sloped. Here it's a steeper bank. But of course, again, that's a function of the meander, because remember, on the outside of the meander, you're going to get steeper erosion. On the inside of the meander, you're going to get deposition of a point bar. We've talked about that because, you know, what's happening is all these little molecules of water, they all want to stay next to their buddies. So as they're going outside, you know, the molecules on the outside of the track are having to speed up in order to stay consistent with the average in the channel cross section. On the inside of the meander, they're going slower because they don't have to go as far. So what happens, again, where it's going slow, you've got deposition. Where it's going fast, you've got erosion. So what that's actually saying is that there's really a delicate balance between erosion and deposition, right? Within one stream. And of course, that's going to be a function of how consolidated the material of the channel is. I mean, if it's hard bedrock, it's not gonna erode the channel so much, obviously, except over very long periods of time. Look, you can see a section of the modern river right over here with my cursor. Watch my cursor. You'll see here comes the headwaters of the river. Right. Oh, here they are right here, coming off of Big Stone Lake, winds around. So this is the Minnesota River coming around, winds around like this, and then flows off the picture. So you can see that the modern river is very small compared to the channel. As I'm saying here, a textbook example of an underfit stream. Note the diminutive size of the modern stream in comparison to the channel it occupies. This is Cottonwood Slough in South Dakota, a relic of the glacial meltdown. So there are dozens. The point is there are dozens of these huge meltwater channels incised into the prairie. And typically the modern streams and rivers occupy those channels because clearly if you've got a stream coming overland and it hits that channel, it's going to flow into the channel and the channel is going to capture it at that point, right? So that's what we've got going on here, underfit streams. And this is the map of the area we've been exploring over the last few episodes, Lake Hind. And look here, here's what we saw earlier. Here's the drainage out of Lake Hind to Brandon. And there's that Assiniboine fan, that big delta fan that displayed out into Lake Agassiz. And actually the flow came from Lake Souris into Lake Hind to the north, and then it flowed out to the south, forming the James Spillway and the Cheyenne Spillway. And over here is the Missouri River. And then you see Lake Regina up here is flowing down past the town of Souris. And then you have the bifurcation of the spillways. One of them is being fed through the Moose Mountain Spillway here, coming from Lake Arcola. So you've got Lake Regina coming this way. The Souris Spillway meets the Moose Spillway. Then it bifurcates again, and then they come back together right down here at Minot. I don't know how to say that, but it's flowing into Lake Souris. So right now, kind of the idea, they say, well, you had Lake Regina catastrophically overflowed into Lake Souris. Lake Souris catastrophically overflowed into Lake Hind, which then catastrophically overflowed into Lake Agassiz. So they've kind of, in a way, kicked the can upstream. You got to ultimately say, well, okay, so you've got this cascading succession of catastrophic overflows of these lakes, but where's all this meltwater coming from, and what was the ultimate trigger for this domino effect here?
You know where those ridges are on that map?
Yeah, they're down. I think they're not actually on this map. They're down roughly down here where it says Proglacial Lake, they're down in this area. Or let's see. Let me get oriented.
I was just
here.
wondering what that Missouri escarpment was, and if there could be any link to whatever that was.
Well, that's a shift in topographical elevation. So I'm thinking, let's see, I'm thinking those linear formations are actually to the east of the Missouri escarpment.
Okay, but yeah,
You'll notice
they were in North Dakota.
Yeah.
Near
So you'll
Minot.
notice
Yeah.
also a flow out of Lake Hind forming the Pembina spillway that comes this way, and then it flowed into Lake Agassiz, forming this Pembina fan right here.
And that's what's behind me. So I'm gonna see if I can take that map and overlay it on what's behind me and see if that all matches up.
Oh, yeah, that would be an excellent exercise right there for sure. No question. Now, this is from Dury back in 1960. He was the one who came up with the term. No, he wasn't. William Morris Davis was the one who came up with the term underfit stream, which was also referred to sometimes as a misfit stream. And Dury kind of revived the term with this 1960 article. And here you can see the sequence of the formation of a large channel. Now, I'm going to actually amend it after we go through the sequence to show you that this is not exactly what we would now think, but we'll go through it. You've got number one, and notice the river size in number one compared to the final river size over here in 3C. You see this? Obviously, this is a much bigger river. However, you'll notice between 1 and 2, 2 and 3, what you're seeing here is that there's a meander, right? Now, there's meanders in a river or a stream have a wavelength, and that wavelength is directly related or proportional to the size of the stream or river itself. So the bigger the river with the greater current flow, the larger the meander you're going to have. What he's showing here between 1 and 2 is basically a uniformitarian process, but simply on a larger scale. You've got a larger river meandering back and forth, and this larger river creates and cuts out a channel. And you can see here that once you get to number 2, you have 2 possible sequences. One, you can go over here to the right and you get 3B, and if you go straight down, you get 3A. And in both cases, what you're going to see here is that what you've still got is a larger channel with a smaller river that's much smaller than the one that cut it. This is more like, for example, what we just saw in the slide I just showed you of the sort of spillway. You've got a very large channel. Now, here's how we would modify this sequence that's being shown here. Rather than the large channel here, like as shown in number 3, actually being incised over a protracted period of time through the meandering back and forth of this larger river, we're looking at a channel that basically was created by one event, or maybe 2 events, but over a very short period of time. So we didn't really have this sequence here. We went directly to creating this right here. In other words, it bypassed all of this, bypassed 1, 2, and 3. Well, 3, let's look at 3. 3 would actually be the latter stages of the bankful flood that would have been flowing across here. If you can picture this diagram right here, filled to the brim at peak discharge, then that water level begins to decline, and somewhere between this being bank full and the stage that's there now, you would have had something about like this. So the way I would modify this sequence is rather than a large river meandering, cutting this channel over a protracted period of time, I would say that this size of the river is basically the declining stages of the mega flood that created the large channel. Does that make sense? I tried to say that in such a way that it might have been semi-understandable.
I semi-understood it.
Okay, that's all that we care about, that you semi-understand it. all you got to do is think about this. Think about this picture being full. Then just picture that the water is draining off, and somewhere between this being full and the modern stage, you would have had a stage like this.
Right.
Right. So
Yeah,
if this is, if this is, say, 30 or 40 million cubic feet per second full, and this is whatever the modern is, which might be, 20 or 30 or 40,000 cubic feet per second, in between that, you're going to have various stages of declining flood volumes.
Yeah,
Right.
this is kind of, I can see this is sort of the South Park uniformitarian idea of how to get the underfit river. It's like step 1, start with a pretty big river. Step 2, step 3, you've got an underfit river.
Yeah,
That's right.
that's kind of it. But hey, in 1960, he was trying to come up with something, and this was a step in the right direction. Let's give him credit for that. It was a step in the right direction.
Yeah, at least he admitted that there was initially much larger flows than there are now, and that's why you.
Yes,
Yeah.
that's right. And this is what he said. This was published in the Geographical Review in April of 1960. A misfit stream is a stream that is either too small or too large for its valley. Now, this is interesting because, as it turns out, there aren't too many examples of something that's too large for its valley.
Yeah.
But he says the fact that misfit streams are regionally distributed seems wholly opposed to the widely held view that they are usually due to capture. Now, what does that mean? Well, what that means is that capture is that, let's say you've got a water flow, you got a catchment basin that's feeding water into the into a creek or a series of creeks that are flowing into a river. And as that river is eroding, let's say it's recessing, its headwaters are receding back. Let's say you've got let's do it this way. You've got a divide here, right? And let's see if I can do this here. I need to look at me, not the screen, because everything is backwards. But okay, so let's say that this is the divide, and the stream is flowing off this way. But as it's flowing off, it's eating its way back into the divide. Now, capture would be if somehow that stream successfully eats its way all the way through and then goes to the other side and gets captured by the stream. And now what it's doing is flowing into the creeks and streams on the other side of the divide. So what it then does is it leaves this valley on this side abandoned. So the assumption is that over many thousands and thousands of years, the stream is slowly enlarging this valley, but it's eating its way back, and it eventually cuts right through the drainage divide. And when it does that, it gets captured by some river or stream that's on the other side. Once it does that, all that water that was previously flowing in this river is now on another side of the drainage in another catchment basin altogether, flowing in a different river. That's the general idea of the capture. And
That's
so,
cool.
yeah, they looked at these large valleys and they came up with the capture model, right? Which, of course, then implies that the valleys, these large valleys, are very slowly created. Okay, so then what Dury is saying is he says that the fact that misfit streams are regionally distributed, in other words, whole regions might have these too large of channels in them. He says that seems wholly opposed to the widely held view that they are usually due to capture. Fieldwork provides consistent evidence that they have been affected by a reduction of discharge. For all those so far investigated are underlain by large alluvium-filled channels that meander round valley bends. Now, alluvium, is material that's been deposited by flowing water. So what he's saying is that the bottom of these channels are all covered with alluvium, stuff that was put there by flowing water. He goes on to say that the reduction of discharge required to make a stream misfit, as calculated from width discharge and width wavelength relationships established by hydrologists, is such to exclude the possibility that valley meanders can be eroded in present conditions. That's an important breakthrough right there. Admitting, you see that's contrary to uniformitarianism, right? That says, well, we extrapolate backwards from existing conditions. And now he's saying that the width discharge and width wavelength relationships exclude the possibilities that they can be eroded in present conditions. Analysis of the discharge/area relationship and field studies of meanders in very small catchments provide particular evidence in support of the general conclusion. It is inferred that the large channels were filled with water, and the valley meanders eroded by runoff supplied in climatic conditions different from those of the present day. And you see, he was, here we are, 40, 50, 60 years ago? Yeah, 60 years ago, more than half a century ago. He's beginning to think in these terms. You see, clearly, this was created in some kind of an environment different than that today. And one of the implications of that is that the climate that was occurring during that period had to have been different than today. So Dury was, he was kind of an important voice at this time that helped to move the discussion away from this strict gradualism. So that was Misfit Streams, the title of that. Misfit Streams, Problems in Interpretation, Discharge, and Distribution. So you can kind of see there, he's recognizing, oh, wait a second. We got some problems here, guys. If we try to explain this strictly in terms of gradualism, we got some problems.
Yeah.
That's basically what he's saying.
Was he saying something about that part of the evidence was that the frequency of the meanders of the small present-day streams couldn't possibly have...
Correct.
Okay.
Yeah. He was saying that within these small catchment basins, how do you get enough water?
Yeah.
See? How do you get enough water to create these huge channels?
Right.
So he's raising some questions, but of course, typically, non-emotive scientific discussions, unless you really kind of get into what they're talking about, you don't realize, hey, this is really pretty amazing thing that he's pointing at here.
Yeah.
These are pretty amazing questions that he's raising. Do another share screen here. Here we go. Okay. If we're seeing this is from that big whaleback outcrop, that sort of big one that I said you could stand up on, and it's kind of in the middle of the spillway, in the outlet spillway. So this picture is taken from the top of that whaleback, and what we're seeing over here is one of the banks of the spillway. And that's probably close to 100 feet topographical difference there between the upland and the bottom of the spillway, which is covered in alluvium, and then scattered throughout the spillway are these big boulders that were probably floated in on icebergs. But so if you turn around and look the other way, on the other side, there's going to be another bank like this. And this defines the outlet spillway. Yeah, so that picture was taken atop this eroded outcrop here. And so, yeah, these are examples of the many kinds of boulders that you see strewn throughout. So notice this is a boulder standing free of the bedrock. And in the background here, you've got a whaleback. You've got bedrock. So
are the boulders and the whalebacks made of the same material mostly?
They appear to be, yes.
Okay, yeah.
So yes, this is standing up on the up on top of the whaleback. And look out here, you see the boulders scattered amongst the trees. You see them over here. Yeah, so that's Big Stone Lake. So it's always interesting when you look at place names, because oftentimes place names can provide clues. All right, so here's whalebacks, and this is bedrock. Now this picture is looking north, right up into what would have been the southern tip of the lake itself. So you're not seeing the banks here. You're looking up into the lake. Yeah, look here. You see this flat area? So you're looking right up into the lake there.
Which lake?
Lake Agassiz.
Agassiz. Okay.
Yeah. The lake, it's not there anymore, obviously. But
it's the lake.
the lake that once was there. Yeah.
Yeah.
So this was the outlet. And now it's these low marshy areas, which is a haven for wildlife. And quite an area. Very impressive. I've always loved the prairies. There's something about them, especially when you get these big skies going on. There we go, a whaleback. So you got to picture the water rushing over this and stripping away. And so one implication of that is prior to the outburst of Lake Agassiz, the surface of the ground was above the top of this whaleback. And in fact, if you go back to the picture where you're seeing the bank, right, with the upland, that upland was the previous surface.
Surface.
Yes, the outlet channel has been cut down into that surface.
That was a good day.
That was a good day. And yeah, the thing that really struck me was, everything about that day for me was good. Although Graham was having a bit of a time because for whatever reason, and it worked good for the rest of us because all the mosquitoes were swarming after him. So,
right.
he was hurrying away. He missed the birds. I got to take him back there so you can see the birds because that was impressive, the birds. I talked about that in a previous episode, so I'm not going to talk about it again other than birds were wonderful.
Well, you saw the gray sky in that picture with the van, though. So you had talked about how it basically followed us for 2 weeks across the whole trip. And then at the last stop there, it cleared out and the sun started breaking through. So it was really quite spectacular there. And sorry you didn't enjoy that as much as we did.
Yeah. Let us go back to screen share. And these are some of the Sichel-Wannen with striations. Let's take a look here.
Oh, yeah.
Now, this is from Jerome's, but notice this kind of parabolic form here, this scalloped form. Now, here you can see its striations, but and check this out. Check out these curvilinear forms here with the sharp rims, as it says here. This is a subglacial. Oh, what's that?
I was going to say they kind of remind me of chatter marks. They got that same kind of curve.
Yeah. Subglacial basinal or basinal S forms. A is Sichel-Wannen with striation in the French River, Georgian Bay, Ontario. Note the sharp crescentic rims and primary furrow flow from lower left. Near field of view, approximately 4 meters. Then, if we look at this, here's what I said. Notice this form right here. You see that?
Oh, yeah.
Look at these here. See these? Now, this is formed, after a rainfall in a nearby creek. You go down by the sandbar, and you can see all of these kinds of flow forms duplicated that you can also see on a mega scale. And so you've got this kind of parabolic profile here. And once you've looked at these and studied them, you kind of get the imagery in your head. Now we'll jump scale so you can see we're going to go to the Palouse lush landscapes of eastern Washington. First, we'll take another look. Take a look. Notice the rounding here. Notice the streamlined depression right here. Mm-hmm. So you can actually have a concave streamlined form. Again, here the rounding is because of eddy currents within the water. Now look at this landscape. Check out, you see this parabolic form right here?
Oh, yeah.
There it is. You see that? Now this is the Palouse Lush. This is taken from the top of Steptoe Butte. And this is one of our stops that we will be making when we eventually and finally get around to doing our Missoula Flood Channel Scablands excursion next spring.
Man, this is beautiful.
Isn't that incredible? Yeah. What you have to picture here is that you've got a sheet flood slowly moving over the land, shaping and rounding and smoothing the loess. Because these loess deposits, that's what this soil is here. It's loess, Loess, and it's anywhere from 100 to 200 or more feet in thickness over the basalt bedrock. But you can just picture the water moving rather sluggishly, because at this point the gradient is very shallow. So the water isn't going to be moving fast, but it's going to be moving rather slow. And instead of eroding and stripping away down to bedrock and then eating down into the bedrock, it's basically just taking and smoothing and hydraulically reshaping the loess into what you see here. And so you could almost look at this, it almost looks like a turbulent ocean in a way.
Yes.
If it was water, see?
Yeah.
But yeah, this was taken from the top of Steptoe Butte, which is an amazing stop on the trip, and we will definitely be hitting that because from Steptoe Butte you get this 360-degree view of the horizon, and you can really begin to get the scale of the thing we're talking about here. Now, of course, this is Missoula floods, which I am rechristening the Cordilleran floods. The reason will become more and more obvious once we start getting into that in detail.
And the teams that have developed that Missoula flood story, that's not really how they look at these hills.
Right.
Right. They don't see it being covered with water and being washed over.
But I mean, the thing is we recall the channels that are cut into that. I mean, Cheney Palouse is cut into this. So it's a normal sequence for a sheet flood moving over land, relatively shallow, to begin to selectively incising a channel. Once it incises that channel, the channel now captures the water. So once the water begins flowing into the channel, it now leaves the other area that was previously submerged. It's now subaerially exposed. Does that make sense? So
I think it makes total sense, but yeah, I think they don't give enough volume of water to have spread beyond the limits of the tracks to also cover the Palouse hills. So yeah, this definitely makes it a bigger event.
Yeah.
Than they're considering.
Yep, I would agree. So I just wanted to tie this back to our trip with Jerome.
Good.
And so we'll do a screen share here. This was that outcrop along the Okanogan River that we find so impressive. This backwash layer's extraordinarily thick, and you guys are looking at the map trying to pinpoint exactly the relationship between this particular massive deposit and the Okanogan Channel. Let's see here if we can maybe back up a bit. Here we go. Look at this, guys.
Man.
This is an amazing outcrop. You see Brad here for scale,
Yeah.
but you've got coarse, you've got bouldery, you've got fine, overcovered by more boulders. I mean, there's a hell of a story there, and we were struggling to try to put the pieces together. But even with Jerome, we didn't really, and to my knowledge, I haven't seen any studies on this particular outcrop.
Yeah, it's right in the middle of the channel, the Okanogan River there coming into. It's actually in Washington. The Okanogan flows out of Canada, but he was describing to us, and I'm hoping we'll get into this next time after we see some of the other. He said there was some new LIDAR, and there's like bed forms, current ripple type forms on the terrace on the outside of the channel. Not far from where this is.
Right.
So, yeah, really interested in looking to how see all that might tie together.
Yeah, there's an amazing story here. If you look, you can see very, very faintly, but nonetheless, there are foresets. You see can you see the faint lines? Okay, those foresets tilt down in the direction of the current flow.
Right.
And yet, when you look at some of the other flows, they look like they're coming from the other way. So this might have been an outcrop where you essentially had
Just washing back and forth.
Yes,
two flows coming together, maybe to
Perhaps.
deposit all that stuff.
Yeah, perhaps that was it. I mean, here you can get a size. I mean, the whole hill
God, that's amazing.
is composed of this material.
Is the hill behind it the same? Like, are they all composed of that stuff?
Pretty much, yeah.
Wow.
Just this one's cut so you can see.
Yeah.
Yes, exactly.
Thanks, road guys.
Yeah.
Yeah, here. This is on the other side,
Whoa.
and you can see it's cut right into the hill. It's like the whole ground is composed of this.
So yeah, it's really hard to grasp, the amount of material that's moving along
Yeah.
at the bottom of however many hundreds of feet of water.
Right.
Yeah.
And it's everywhere. It's all over the place. So it's just being moved around, but it's nicely exposed there. And yeah, it definitely makes you scratch your head.
Yeah, that would be the kind of thing that somebody could actually go and spend a year or two on that outcrop doing their PhD thesis.
Definitely.
So Kyle, get busy.
Students.
I'm in the winemaking business now, man.
For at least another month.
But I was
Great
noticing
stuff.
some pretty interesting, like I've had this one bit of white wine settling for a long time in this glass jar. It's a small, like, last little bit that I had, and it's in a 1 gallon glass carboy. And I had to stir in some of the preservative, the SO2, and I stirred it just a little bit because there's a tiny, tiny fine layer of the lees at the bottom. And I got the water spinning, and then at the bottom, it just started picking up that lees into this beautiful form. And I just sat there and watched it for like 5 minutes turn into this amazing thing, and how it turned it over and created all these different little geometric patterns out of it as the whole thing is like slowly moving around inside the jar. It was really, really cool. And that's what I was thinking of the whole time, is like, okay, floods on these massive scales can pick up huge objects, and they're going to be doing all kinds of crazy geometrical, forms at the bottom and setting it down in those ways. It was pretty cool to watch.
So in closing here, I want to say that check out, we got these really cool t-shirts. So what I want everybody to do that likes the show, buy a t-shirt, put it on, take a picture of yourself and send it to us.
There you go.
And
That's
we'll take 5 minutes on one of our upcoming episodes, and we'll see everybody in their Kosmographia t-shirts.
That's cool. Yeah.
That's a
That'd be
great
awesome.
idea.
Yeah. That way we can get to know who we want to know. You guys, you see us and our faces, but who are these anonymous listeners out there? We want to know you guys. We want to have a big old party and invite several tens of thousands of you to the party and get to know all of you. I want to close here with one of my favorite pictures that I think you'll like this, because this was after 9 or 10 days of like trying to stay ahead of the rain. We finally got to the Badlands and we started having some decent weather. And so let me pull this up, and we'll just do this.
And we can have 50 bands there, and we'll call it Carlson Stock.
Carlson stock. Yeah. Yeah. Carlson stock.
Randall Cella.
Oh yeah, that's a great photograph.
Isn't that a great photograph?
Hey.
Yeah. Although you can see it's still overcast. At least it wasn't raining.
Yeah, we didn't get to spend enough time there, that's for sure.
Yeah.
We just flashed by.
Yeah, we were in a hurry to get to Minneapolis, so we didn't get to spend nearly enough time in the Badlands. But we'll be coming back and talking about the Badlands. Absolutely.
Awesome.
How come the Badlands got bad? That's what we're going to talk about.
And the nearby sand hills.
Oh yeah. God, we got so many things to talk about. We got to start
Lots
doing,
to talk
I think,
about.
we're going to have to pretty much start doing daily episodes.
Yeah,
I mean, how else are we going to ever cover all this material?
that's
mean,
right.
When are you going to publish the course syllabus?
I'm trying to get there. That's why we're trying to expand the team a bit here.
Buy those t-shirts.
Yeah, buy those t-shirts. Yep.
Yeah. So where do they get the t-shirts? RandallCarlson.com.
You can go to randallcarlson.com, and then of course, we're partnering with HowTube.
That's right.
Which is pretty awesome. We want to see HowTube supersede YouTube without all the political correctness and censorship and stuff that's now happening on the other platforms.
Yeah.
The idea behind it is, we're not going to allow a whole bunch of trash talk, but when it comes down to the idea, down to the concept of ideas, it's going to be wide open. If you come on there and you start calling people a bunch of names and this and that, that ain't going to cut it. But the idea is to be able to come on there and express a diversity of ideas and viewpoints without being censored just because you're expressing some particular viewpoint that is not currently the fashionable dominant viewpoint. So it's a really interesting concept. So, if you go to randallcarlson.com, you're going to be able to find the link right there to HowTube and begin learning about this new platform that we are privileged to be associated with. And using this podcast is actually one of the flagship podcasts. So hopefully, we are starting something here that's going to grow significantly. And all of you guys that are, the first fans and viewers, you'll go right along with us as this thing grows and we start getting access to more resources. And what we did with Jerome, I hope is just the beginning. I think it is. We're going to be getting a lot of interesting people on here over the next few months to a year to educate us, to be able to dialogue with them about their particular research and how it may fit into this rapidly changing, dramatically changing paradigm that we're living through right now. So, yeah, I'm excited. And I'm doing a written blog, and the blog, sometimes it might be independent of the podcast episodes, but other times it may be fleshing out or extending some of the ideas that we're covering in the podcasts. It's also going to have images and graphics and illustrations and things that will be embedded in the blog. And we're doing something new where I'm doing audio versions of the blog, and Kyle is setting a really cool music backdrop to it. And I think that's going to be a pretty awesome thing that, people will be able to download, listen to while they're driving or, washing dishes or walking their dog or whatever, So that's happening, and a lot of other things are happening too.
Yep. Lots of new stuff going on with the new website. So it's great. Everybody should check it out.
Yep.
And everything else is in the show notes. Thanks, everybody, for watching. We love all of you. Thanks for everybody supporting the show.
Yeah, many thanks to the ongoing Patreon supporters. Yeah, big
absolutely, guys. You guys that are helping us out with that. Yeah, it really is. It really is a help and really appreciated.
That's right.
And we're going to figure out something to do special for all of those of you that are supporting us that way.
That's right. We're working on it.
We're working on it.
All right, guys. Great show. See you next week.
Yep. Great job.
Good night.
Thanks, y'all.
Good night.
Good night.
Good night.